So we have a function here, gamma of n, that's defined by an indefinite integral, and we want to show that the function has this property. Now, at first glance, this may seem like just another textbook exercise type question, but this gamma function actually has a really interesting property that we'll talk about on the next slide after we've shown that this property really does apply to it. So I'm going to do this using integration by parts. So I'll let u equal x to the n minus 1 and dv equal to e to the negative x dx. And we'll do what we do with integration by parts. We'll differentiate the left side, integrate the right side, and we end up with this. Du equals n minus 1 x to the n minus 2 dx, and v is equal to negative e to the negative x. So if I substitute those into the integration by parts formula, remember that's uv minus the integral of v du, we get this expression. The left-hand side is just the original gamma of n formula, right? And that equals this integral on the right-hand side. Now, looking at the integral part, that's integrating with respect to x, not n. So I can take that n minus 1 and bring it out in front. And now notice how I rewrote the exponent. Right? I rewrote that as n minus 1 minus 1, because if you compare that back to the original formula, back in the question, and if you take the original formula and replace the n's on both sides with n minus 1, you get gamma of n minus 1 equals that integral that I have right here. All right, so if I make that substitution, the whole integral part goes away, and all that's left is to evaluate the left-hand part of this. Now, obviously, if you look closely, the stuff to the right of the plus sign is the formula that I'm looking for. So I'm really hopeful that that integral there is going to end up equaling 0. So this is where the actual improper integral part comes in, right? I'm going to rewrite this as the limit as b goes to infinity of that expression minus, and I'm going to take that expression and I'm going to substitute 0 in there. Okay, now this limit, the limit goes to 0, right? E to the negative b is 1 over e to the b, and that exponent is increasing a whole lot faster than negative x to the n minus 1, which, with respect to b, is actually constant, right? And this right-hand part, obviously, that just evaluates to 0, right? Which is awesome. So all I'm left with is gamma of n equals n minus 1 times gamma of n minus 1, which is exactly what I wanted. Okay. So why is this function significant? Well, remember we have this factorial function. N factorial is equal to n times n minus 1, n minus 2, all the way down to times 2 times 1. In other words, you're multiplying together all the integers between 1 and n. So here's what I want you to think about, right? How about if we try to evaluate gamma of 5? Well, my formula says that gamma of 5 is equal to 4 times gamma of 4. But my formula also says that gamma of 4 is equal to 3 times gamma of 3. Gamma of 3 is 2 times gamma of 2. Gamma of 2 is 2 times gamma of 1. And you can go back and you can work this out for yourself if you like. If you substitute n in there for 1, it becomes gamma of n x to the 0 e to the minus x. You can work through that integral on your own if you like, and you should see that gamma of 1 is actually equal to 1. So that means gamma of 5 is equal to 4 times 3 times 2 times 1, which is 4 factorial. Right, so hopefully you see we can generalize this and say gamma of n is equal to n minus 1 factorial, and this is why this function is so interesting. Right? For any integer, be specific about this, any non-negative integer, gamma of n is equal to n minus 1 factorial. However, the original gamma of n function is continuous and defined for all real numbers. So what we've done here is we've found a way to take the factorial function, which is only defined for discrete numbers, right, for discrete non-negative integers, and we have extended that into a continuous function that's defined for all real numbers. Right? So this gamma function, this is not just a textbook question. The gamma function really is a well-known thing, right? And it has this really cool property that it extends the factorial function up to a continuous function.